You know that very specific, incredibly universal knot in your stomach that forms right around the first real cold snap of the year.
Oh, absolutely, yeah.
Right. You walk over to your hallway thermostat, you push the dial up, you hear that familiar mechanical click of the furnace kicking on, and instead of just feeling relieved that warm air is coming, you instantly start doing mental math.
You're picturing your energy bill.
Exactly. You're picturing the bill. Because the sheer skyrocketing cost of energy right now, plus these severe deficits we are seeing in natural gas. I mean, it's shifted from a macroeconomic news headline into a literal physical pain point hitting your bank account every single month.
It really has.
Mm.
And, it's fundamentally altering how we interact with our own living spaces.
Yeah.
I mean, for decades, we've basically operated under a model of passive consumption.
Right.
Whatever fuel a utility company piped into the neighborhood, be it gas, oil, or electricity, we just accepted it and, paid the fluctuating premium.
We didn't really have a choice.
Exactly. But that era of unquestioning reliance is ending, and it's happening purely out of financial necessity.
Which brings us to the escape hatch. Because today we are pulling from a massive, highly technical engineering guide on autonomous heat supply systems.
A very dense guide, I should add.
Oh yeah, super dense. We're looking specifically at theme 7 of this breakdown, which focuses entirely on heat pumps. But we are going to skip the dry academic jargon and just head straight into the core mechanics.
Good call.
Our mission for this deep dive is to decode the actual physics of how these machines work, map out the different variations available, and really help you, the listener, figure out how this technology fits into your specific home.
Because it's not a one-size-fits-all situation.
Right. Because before you sign a massive check for your next major home upgrade, you need to be armed with the facts. No contractor double talk. So, okay, let's unpack this, because on the surface, this technology sounds completely fabricated. It sounds like magic, but it's actually just brilliant thermodynamics.
Yeah, magic is it's the most common reaction when people first encounter the performance metrics of a modern heat pump. To truly grasp how they achieve these numbers, we basically have to unlearn a century of human conditioning regarding how we heat our environments.
Okay, let's start right there with the core illusion of the heat pump. Because when I think of heating a house, I think of a furnace. And a furnace, at its most basic caveman level, is just building a fire inside a metal box.
Right, and that is the crucial distinction here. A traditional furnace, whether it's combusting natural gas, burning heating oil, or even if it's a standard electric resistance baseboard heater, it operates on the principle of production.
Making heat.
Exactly. It consumes a fuel, destroys it through some chemical or electrical process, and the resulting byproduct is thermal energy. A heat pump produces absolutely nothing.
Nothing at all.
It does not create heat.
Yeah.
It merely moves it from one location to another.
It just relocates thermal energy that already exists. So to do that, the engineering text breaks the system down into a closed hydraulic circuit utilizing a specialized liquid, right? A refrigerant.
Which is essentially your kitchen refrigerator, but engineered to work inside out.
Right. So the guide outlines 4 main steps, starting with the evaporator, which sits outside your house and absorbs heat from the ambient air or the ground. But wait, I have to stop you there, because this is the mental roadblock for most people.
The freezing air problem.
Yeah. If it is 5 degrees below freezing outside in the dead of winter, how on earth is the evaporator absorbing heat from air that is already freezing cold?
I know, it seems totally counterintuitive until you factor in the relationship between pressure and boiling points.
Right.
Like, we're all used to water boiling at 100 degrees Celsius, right?
Right.
But that's only true at sea level atmospheric pressure. If you go to the top of Mount Everest, where the air pressure is way lower, water boils at a much lower temperature.
Okay.
The heat pump basically weaponizes this principle. In the evaporator sitting outside your house, the system maintains the refrigerant at an extremely low pressure.
So it's like a fake Mount Everest inside the pipe?
Yes. Because the pressures drop so drastically, this liquid refrigerant boils and turns into a gas at a temperature far colder than the freezing winter air outside.
I get it. So because the liquid inside the pipes is technically colder than the freezing air outside the pipes, the thermal energy naturally wants to flow from the air into the liquid.
Right.
It captures that, like, microscopic amount of ambient warmth.
Exactly that. I mean, even sub-zero air contains thermal energy. So the refrigerant absorbs that energy, evaporates into a gas, and then flows into component number 2, the compressor.
The compressor.
Yeah, this is the mechanical heart of the whole operation. The compressor takes that low-pressure gas that's holding the absorbed environmental heat and aggressively squeezes it.
And compressing a gas drives up the temperature. Like when you're aggressively pumping up a bicycle tire manually, the metal cylinder of the hand pump gets physically hot in your hands.
That is the exact physical mechanism at play.
Yeah.
By drastically raising the pressure of the gas, the compressor elevates its temperature to a highly usable level.
Wow.
This intensely hot gas then flows into the third component, the condenser, which is located inside your home's actual heating infrastructure. So the hot gas passes through a heat exchanger.
Okay.
And because this gas is now significantly hotter than the water in your floorboards or the air in your ductwork, it eagerly transfers its heat into your home.
And as it dumps that heat into my living room, the gas cools down and condenses back into a liquid state.
Which brings us to the final hurdle, component number 4. Because the system has to reset.
Right.
This high-pressure, room-temperature liquid hits the expansion valve. The liquid is basically forced through this tiny restriction, which drops its pressure instantaneously on the other side.
Oh, I know this one. It's like when you buy a can of compressed air to blast the dust out of your computer keyboard.
Yeah, exactly.
When you hold the trigger down, the pressure inside the can drops rapidly, and the can gets freezing cold in your hand.
A perfect analogy. The sudden pressure drop in the expansion valve causes the temperature of the refrigerant to plummet back down to an ultra-low sub-freezing state. It flows back outside to the evaporator, and the entire cycle repeats endlessly.
So it's basically a thermal smuggler.
A thermal smuggler, I like that.
That is the best way to visualize this for you listening. It refuses to build a fire in your house. Instead, it sneaks outside, grabs whatever tiny microscopic traces of heat exist in the freezing winter air, hides that heat in refrigerant, smuggles it through the wall, squeezes it until it's hot enough to actually feel, and just drops it off in your hallway.
A thermal smuggler captures the mechanics beautifully.
Yeah.
And because it operates as a mover of energy rather than a creator of energy, we arrive at the metric that makes traditional furnaces completely obsolete.
Let's talk numbers.
Right. The source text highlights the coefficient of performance, or COP, because you are only paying the electric company to run the compressor and the pumps. You aren't paying for the heat itself. 1 kilowatt of electrical energy used by the system can deliver roughly 5 kilowatts of heat energy into your home.
See, that is the ultimate aha metric right there, a COP of 5. For every single unit of electricity you buy, you get 5 units of heat out.
It's staggering.
Because a top-of-the-line brand new natural gas furnace can never, ever exceed 100% efficiency.
Right.
It physically cannot yield more energy than what is stored in the chemical bonds of the gas. But this smuggler system is giving you 500% efficiency.
Which fundamentally rewrites the economics of domestic living.
Okay, so if the heat pump's sole purpose in life is to steal heat from the surrounding environment, the obvious question for you, the listener, is where is it stealing from? Because the source text makes it very clear that you have choices here.
You do. And the text categorizes these into 5 main archetypes, primarily divided between closed cycle and open cycle systems. These are defined entirely by the source of the thermal energy.
Okay, let's look at the closed cycle options first. The text mentions ground and water sources.
Right. Within closed cycle, you could opt for a horizontal geothermal system. This involves laying a massive, sprawling network of pipes buried just below the frost line across a wide expanse of land.
Okay.
Alternatively, if you lack horizontal space, you can use vertical geothermal, which requires bringing in heavy drilling rigs to bore hundreds of feet straight down into the bedrock to sink the pipes.
Wow.
And the third closed cycle option is water-based, where you take a massive closed loop of piping and sink it to the bottom of a large, stable body of water.
And the open cycle system.
That is also water-based, but instead of a sealed loop of fluid gathering heat, the system actually pumps physical groundwater from a well or surface source, extracts the thermal energy from it directly, and then discharges the chilled water back into the local environment.
Okay, I have to jump in and heavily push back on this menu of options.
Fair enough.
Because these sound like absolute logistical nightmares. I mean, if you are a normal person living in a standard suburban neighborhood or a townhouse, you don't have an acre of land to dig a horizontal trench field.
No, most people don't.
You probably don't have the geological clearance to bring in an industrial drilling rig for a vertical borehole. And you certainly don't own a private deep-water lake.
Well, the authors of the text anticipate exactly that reaction. They dedicate a significant portion of the guide to validating those hurdles. Ground and water source heat pumps require staggering upfront capital expenditures and incredibly disruptive construction works.
Not to mention the bureaucratic red tape. I can only imagine the permits.
Oh, the environmental compliance is immense, particularly for the open water systems. You are physically pumping groundwater, altering its temperature, and introducing it back into the water table. Environmental protection agencies monitor that rigorously to prevent ecological damage.
Makes sense.
So that combination of high cost, massive space requirements, and ecological red tape is precisely why the text pivots hard to emphasize the fifth category, the air source, specifically the air-to-water heat pump.
Right, the air-to-water heat pump. This one skips the earth and the lakes entirely. It extracts heat directly from the outside ambient air and transfers it into your home's internal hot water system, which feeds your radiators or underfloor heating.
Exactly. It bypasses almost every major installation hurdle. You do not need earth-moving equipment, you don't need a pristine aquifer, and you don't need a massive yard.
You just need a wall.
You just require a small exterior footprint, roughly the size of an air conditioning condenser, placed outside your home. It really democratizes the technology, making it incredibly accessible for standard residential retrofits.
So, assuming air-to-water is the most realistic path for the listener, why go through the hassle of ripping out your old, reliable gas furnace at all? I mean, beyond the 500% efficiency, what is the actual day-to-day benefit?
Well, the guide details a cascading series of advantages. Ecologically, there is zero localized combustion, meaning zero emissions on your property. From a safety standpoint, you are entirely eliminating the risk of explosive gases or carbon monoxide leaks in your living space.
That's huge.
And for anyone building a new home, the capital cost reduction is surprisingly large because you completely eliminate the need to run municipal gas lines, install gas meters, or pay connection fees to a utility provider.
But the text mentions something else, and this is where it feels like you're unlocking a cheat code for your house. It's the total system benefit of summer and winter double duty.
Oh, yeah. That stems from the reversible nature of the thermodynamic cycle.
Let's break that down, because a standard air conditioner just takes the uncomfortable heat from your living room and blasts it out into the hot street.
Right.
It just wastes that thermal energy. But the text explains that in the summer, a heat pump runs in reverse to cool your house. And instead of throwing that extracted indoor heat away, it diverts it.
Yes. It captures that waste heat and injects it directly into your domestic hot water cylinder, or even a swimming pool if you have one.
That's amazing.
You are already purchasing the electricity to run the compressor to air condition your living room. The byproduct of that cooling process is heat. So by capturing it, the system essentially provides you with free domestic hot water for your sinks and showers all summer long.
Free hot water, just as a byproduct of staying cool. It's brilliantly efficient. But that leads us directly to the massive engineering elephant in the room.
The winter problem.
The winter problem. Because I know you listening are probably thinking summer sounds great, but what happens in January? How does an air-to-water heat pump keep a house warm during a massive blizzard without just eventually failing and freezing the pipes?
Managing extreme cold is definitely a primary design challenge of air source systems. To solve it, the engineering guide introduces a critical technical threshold known as the bivalent point.
Bivalent. Let's decode the jargon. Bi meaning two. Is this the specific point where two different heating systems have to tag team to keep the house warm?
That's a great way to conceptualize it. The building codes outline the bivalent point as the exact minimum outside temperature at which the heat pumps thermal output perfectly, 100% matches the heat loss of the building.
So it's a tipping point.
Yes. If the outside temperature drops even half a degree below that specific bivalent point, the heat pump can no longer carry the thermal load of the entire house by itself. It needs supplemental help. The text cites recommendations from major manufacturers, like Wolf, who explicitly advise against buying a heat pump massive enough to handle the absolute coldest day of the year.
Really?
Yeah. If your region hits negative 10 degrees Celsius once a winter, Wolf recommends setting your bivalent point much warmer, around -2 to -5 degrees.
Wait, why wouldn't you just buy the biggest unit possible? Wouldn't you want a heat pump that can easily laugh off a -10-degree blizzard on its own?
Because doing so creates a financial and operational disaster.
How so?
If you size a heat pump to handle -10 degrees, you are purchasing massive, incredibly expensive equipment that will be wildly oversized for the other 95% of the winter when it's only slightly chilly. An oversized heat pump will constantly short cycle, basically turning on and off rapidly, which destroys its efficiency and wears out the compressor prematurely.
Okay, that makes sense. It's like buying a massive commercial dump truck for your daily highway commute, just in case you need to move a sofa once a year.
Exactly.
But if you size it smartly for -4 degrees, what actually happens when that rare -10-degree blizzard hits? Do you just freeze on the couch?
Not at all. That is where system configurations come into play. The text lays out 5 distinct operating modes to handle these temperature drops, giving homeowners a menu of choices based on their existing infrastructure.
So how do we choose?
Well, if you're one of the lucky few who installed a deep vertical borehole, the ground temperature hundreds of feet down never changes, even during a blizzard. In that case, your heat pump runs solo all year round. That is called monovalent operation.
But for the rest of us using the air source units, we need a backup. What's the simplest fix? Do you just add a massive electric heater?
You can. That mode is called monoenergetic. The system relies on the heat pump, but features a supplemental electric resistance heater, essentially a giant high-voltage toaster coil installed directly inside the water tank.
A giant toaster coil, got it.
On those rare, brutally cold days, that electric element kicks on to make up the difference. The text notes this coil is also periodically used to intentionally spike the hot water temperature to kill off bacteria like Legionella.
But running a giant toaster coil uses a lot of electricity. What if you live in an older home and you already have a gas boiler in the basement?
Then you look at the bivalent modes. You can run bivalent parallel where the heat pump runs constantly, but when the blizzard hits, the old gas boiler wakes up and they run simultaneously, sharing the load. Or you could use bivalent alternative, which is a clean handoff. The heat pump handles everything during mild winter weather, but the moment the temperature hits the bivalent point, the heat pump completely shuts down and the gas boiler takes over 100% of the work until the weather warms back up.
Which brings up the absolute biggest anxiety for anyone living in an older house, because older homes usually have those massive, heavy cast iron radiators mounted to the walls.
All right.
And those old radiators require water heated to roughly 90 degrees Celsius to actually radiate enough heat. But earlier, you said heat pumps are designed for low temperatures. They operate most efficiently when making water that's only about 55 degrees Celsius. So does putting in a heat pump mean you have to hire a demolition crew to rip out every pipe and radiator in your house? Because that sounds like an absolute nightmare.
The guide addresses this exact fear, and the solution is deeply reliant on modern insulation. It is true that traditional radiators were designed for 90-degree water, but we have to ask why they needed to be that hot.
Right.
Historically, they were over-engineered to compensate for incredibly drafty, poorly insulated buildings. They were basically fighting a losing battle against heat loss.
Okay, so the house was leaking heat like a sieve, so the metal had to be dangerously hot to keep the room comfortable.
Precisely. The aha moment for homeowners is this. If you have recently upgraded your home's thermal envelope, say you've blown modern insulation into the attic, or upgraded to double-pane windows, your home's total heat loss has plummeted. The building actually holds on to energy.
Oh, because the room isn't constantly leaking heat out the window, that old cast iron radiator doesn't need to hit 90 degrees anymore.
That is exactly it. You keep the old radiators. But because your house is now properly insulated, those same cast iron radiators can easily keep the room perfectly comfortable, using only the 55-degree water supplied by the heat pump. You completely avoid the plumbing tear-out.
That is a massive sigh of relief. But just to play devil's advocate, what if it's a historic home? What if you physically cannot insulate the walls and the radiators absolutely demand 90-degree water on a cold January night?
That is where the bivalent alternative mode saves the project. You install the heat pump, but you don't throw away your gas boiler.
Right.
For 80% of the winter, when it's just mildly chilly, the heat pump easily supplies 55-degree water, which is enough to keep the chill off. But during a deep freeze, when the house is losing heat rapidly and those radiators absolutely must hit 90 degrees, the heat pump simply turns off.
And the boiler wakes up.
The gas boiler kicks on, blasts the high-temperature water, and you stay warm. You get the 500% efficiency and environmental benefits of the heat pump for the vast majority of the year without having to rebuild the historic interior of your house.
It is an incredibly adaptable piece of engineering. So let's recap the journey we've just taken through this engineering guide. We started by demystifying the thermodynamics, understanding the magic trick of the compressor and the expansion valve that allows us to move heat rather than create it, granting us that staggering COP efficiency.
That 500% efficiency.
Exactly. We explored why the air-to-water system allows regular homeowners to bypass the absurd requirement of digging up their yards or sinking pipes into a lake. We looked at the summer cheat code, where cooling your living room gives you free domestic hot water. And we finally solved the winter freezing problem, learning how choosing the right bivalent setup lets you survive a blizzard and keep your vintage radiators.
It is a comprehensive technological shift. I mean, we are moving away from combustion entirely.
And that is why digging into this material matters for you, the listener. Understanding these concepts is your shortcut to being genuinely well-informed. The next time you feel that cold draft, or the next time you have a contractor standing in your basement quoting you for a home energy upgrade, you won't be blinded by technical jargon. You know what a bivalent point is. You understand the physics of a refrigerant. You hold the cards now.
And, the guide leaves us with one particularly fascinating implication. Zooming out from the individual house to the macro level, it mentions the concept of full autonomy.
Full autonomy.
Yeah. If we project this technology forward, imagine an entire suburb or a whole city adopting this. If millions of individual homes transform into their own autonomous, highly efficient heating and cooling power plants, they completely detach from the need for massive, centralized utility pipelines.
Wow.
How will that shift toward a decentralized, independent thermal grid alter the way we plan infrastructure, build cities, and manage national energy security in the future?
That is a brilliant final thought. Are we shifting from a world reliant on massive, vulnerable infrastructure grids to a resilient web of millions of independent thermal smugglers? Something to mull over as you enjoy your next unexpectedly cheap, heat pump-powered hot shower. Thank you for joining us on this deep dive. Keep questioning the world around you. Keep pushing for the why behind the facts. We'll catch you next time.